In section 6.6, we'll discuss how energy changes are measured using two types of calorimetry. We'll talk first about how to use the principles of calorimetry to calculate the heat transfer between two substances. We'll then move on specifically to constant pressure and constant volume calorimetry. Let's begin. Calorimetry is the study of heat transfers by measuring the temperature changes in the substances involved. For example, a piece of hot metal placed in cold water will see the metal cool as the water warms. Eventually, the metal and the water reach thermal equilibrium as they achieve the same final temperature. We can quantify the amount of heat lost by the metal as being equal to the heat gained by the water, assuming no heat transfer to the surroundings. Let's work through an example to demonstrate. Suppose we add 6.8 grams of aluminum metal at 67.4 Celsius to 195 grams of water at 19.6 degrees Celsius. What is the final temperature of the system when thermal equilibrium has been achieved? To solve this, we know the heat lost by the metal, which will have a negative value, is absorbed by the water, which will have a positive value. So Q sums to 0. We need the final temperature, so we split delta T into its component parts, recognizing that T final is the same for both the water and the metal. Using the equation from the last slide, we can substitute in the known quantities: 195 grams of water, the specific heat of water, the initial temperature of the water, the mass of the metal, the specific heat of the metal, and the initial temperature of the metal. Multiplying everything through, we get 815.9 joules per degree Celsius times T final minus 15,991 joules for the water part of the equation, and 6.066 joules per degree Celsius times T final minus 408.8 joules for the metal part of the equation. Next, we combine like terms, which gives us 822 joules per degree Celsius, rounded to 3 sig figs, and 16,400 joules, rounded to 3 sig figs. Solving for T final means we need to divide both sides by 822 joules per degree Celsius, giving us 19.95134 degrees Celsius, which, rounded to 3 significant figures, is 20.0 degrees Celsius. Here's one for you to try. Hot metal is placed in cold water with initial and final temperatures recorded. We know the heat lost by the metal is equal to the heat absorbed by the water, so I've supplied that equation here. First, determine delta T water and delta T metal. Now, substitute delta T values, masses, and the specific heat of water into the heat equation. Solve for the specific heat of the metal. Identify the metal. Here, chromium, cobalt, and iron are all possible answers. Constant pressure calorimetry is commonly done using styrofoam cups and a lid to minimize heat transfer between the system and surroundings. The system is not sealed, so the calorimeter pressure is the atmospheric pressure, meaning that it's considered a constant pressure calorimeter. This type of system makes it easy to measure Q sub P for any heat transfer that can happen in aqueous solution. From our last lecture, recall that Q sub P equals delta H, the enthalpy change for the reaction. The release or absorption of heat that occurs when a solid compound dissolves in a solvent at constant pressure to infinite dilution is known as the enthalpy of solution, delta H solution, or heat of solution. The heat of solution, Q sub solution, will be equal in size but opposite in sign from Q sub P, the heat associated with a reaction under constant pressure. Both reaction enthalpies and heats of solution are commonly measured using constant pressure calorimetry. Let's look at an example. Suppose we dissolve a small amount of potassium chloride in 100 milliliters of water inside a constant pressure calorimeter. While the solid is dissolving, the temperature drops from 20.1 to 17.4 degrees Celsius. We're asked to determine the signs of Q's solution, Q under constant pressure, and to decide if the reaction is endothermic or exothermic. Let's examine the evidence. The temperature of the solution drops, which we can express as T final less than T initial. This means heat is moving out of the solution, so Q of solution is less than 0. We also know that Q of solution is equal to negative Q sub P, meaning that Q sub P is positive. Therefore, the process is endothermic as heat moves into the reaction. In this example, we have 25 milliliters of a strong acid added to 25 milliliters of a strong base. The solution temperature increases from 20.5 to 25 degrees Celsius during the neutralization reaction. We're asked to calculate the enthalpy change of this reaction. To do so, we need the mass of the combined solution. Next, we calculate the heat transfer. Assuming the strong acid has a concentration of 1.5 molarity, calculating the enthalpy change per mole of acid requires us to calculate the moles of acid so we can divide the enthalpy by that result. The second type of calorimetry we'll discuss is done under constant volume in a bomb calorimeter, which is so named because they are designed to withstand high temperature and pressure changes and to be sealed and insulated from the surroundings, making them close to a true isolated system. Heat flow in a bomb calorimeter is a measure of delta U, where delta U equals Q plus W. We know that W equals 0 inside a rigid container with a constant volume, since no pressure volume work can be done. Therefore, delta U equals Q sub V, the heat flow at constant volume. If you'd like to see how a bomb calorimeter works, consider working with the bomb calorimeter activity in Figure 6.13 from the textbook. We must consider the total heat capacity of the calorimeter, capital C sub cal, and the specific heat of the water used inside it, since both will absorb heat from the reaction. C sub cal is measured for each calorimeter with an accurately measured volume of water inside. This becomes a constant for a given bomb calorimeter that must be supplied to calculate the heat of a reaction. This gives us several important relationships. Q of solution equals C calorimeter delta T. Q solution equals negative Q sub V, which allows us to say Q sub V equals negative C sub cal delta T, and delta U of reaction equals Q sub V equals negative C calorimeter delta T. Let's practice. Lactose and oxygen are reacted in a bomb calorimeter. The temperature increases by roughly 9 degrees. To determine the signs of Q solution and QV in this reaction, we can use the relationship Q solution equals C calorimeter delta T equals negative Q sub V. Delta T is positive, so Q solution is positive, and Q sub V is negative. Determine whether the reaction is endothermic or exothermic. Q sub V is negative, so the reaction transfers heat to the solution and is exothermic, as we saw by the increase in temperature. A 1 gram sample of decane is ignited in a bomb calorimeter, causing the heat to rise from 20 degrees Celsius to 78.8 degrees Celsius. We're asked to determine delta U of reaction for the combustion of decane in units of kilojoules per mole of decane. To do this, we'll first calculate the heat transferred as Q sub V equals negative C calorimeter delta T. Next, we'll divide Q sub V by the number of moles of decane combusted. As always, I'll leave you with the parting thoughts of the authors.